This Zoom session is being brought to you by the Fractal Globe Snow Ring W. All right, for today, we'll be covering two sections, one of them an extra credit section, 5.2, and the other 5.3, the complex plane and de Moivre's theorem assigned. So, hold on. He is entered. Let me make a note here. All right. Now, okay, this is a section about polar coordinates and polar equations and graphs. It's extra credits, so I won't really go over the homework much, but here's how it works. Okay, polar coordinates for a point give you r, the distance up from the origin, and theta, its angle from the positive x-axis. The rectangular coordinates give you x, the horizontal distance from the origin, and y, the vertical distance from the origin. These two relate by these two sets of conversion equations. From polar to rectangular, you have x equals r cosine theta and y equals r sine theta. To go from rectangular to polar, it's a little more complicated. R is root of x squared plus y squared. That's unambiguous. But theta, it depends upon which half of the plane, the right half or the left half. For the right half of the plane, where x is positive, theta is arctangent of y over x. For the left half of the plane, theta is pi plus arctan y over x. Okay, we can use these identities to convert polar equations to rectangular equations and vice versa. For example, radius equals a. That's a circle of radius a. Well, that's root of x squared plus y squared equals a. Therefore, x squared plus y squared equals a squared. This is the rectangular equation for this polar equation, r equals a. Okay, this is a circle with center 0 by 0 and radius a. Here, theta equals a. This is at a specific angle. It's on a line at a specific angle from the horizontal. So arctan y over x equals a, so y over x equals tangent a, so y equals x tangent a. That's a line through the origin, 0, 0, at an angle a. R equals a cosine theta. All right, now this is a little more complicated. If you multiply both sides by r, you get r squared equals ra cos theta. R squared is x squared plus y squared. R cosine theta is ax, so it's x squared plus y squared equals ax. That's the rectangular equation, which after a few steps, transpose the ax, add a squared over 4 to both sides, you get the equation x minus a over 2 all squared plus y squared equals a over 2 all squared. This is a circle with radius a divided by 2 through a over 2 by 0 and 0 by 0, looking like this. For r equals a sine theta, much the same thing happens, only with a y. So it's x squared minus x minus y minus a over 2 all squared equals a over 2 all squared. That's a circle with radius a over 2 through 0 by 0 and 0 by a over 2. R cosine theta equals a. Well, that's easy enough. R cos theta is just x, so this is x equals a vertical line at a distance at x equals a, through x equals a. R sine theta equals a, that's the same as y equals a, this horizontal line at height a. Now, it gets more complicated when you get more complicated equations. For r equals a plus or minus b cosine theta, it depends upon which is bigger, a or b. They're all three what are called cardioids. If a is bigger, you get this kind of little dented circle. If b equals a, then it comes to a sharp point like that. And if b is bigger than a, then it does a loop-de-loop like that. Just a moment. Chase, so that's edge, I do believe. Yes. Right. R equals a sine 3 theta. Well, you get a 3-petaled rose. They give some examples. R equals 4, circle of radius 4. Theta equals pi over 3. This is this line at tilted at 60 degrees. R sine theta equals 4. It's a horizontal line like this at height 4. R cos theta equals negative 2. It's a vertical line at x equals negative 2. R equals 2 cosine theta, a circle tangent to the origin like this. R equals minus 4 sine theta, a circle like that. Okay, I'll leave that with that. That's it really is. Some of the more complicated ones, like for example this, really the best thing to do is to use your calculators polar coordinates graphing if you have a calculator which does that. This is why I made it an extra credit assignment. But we move on to 5.3. The complex plane and de Moivre's theorem. Big stuff. Okay, complex plane denoted by a fractal C. It's a plane, it's a number plane. It includes it at the number line, the real number line, -2, -1, 0, 1, 2, 3, 4, and so on. But it also includes the square root of -1i and the opposite of I, minus I. And it also includes points off these two lines. 1 plus I is over 1 and up I. So that's how that goes. If a number is in the complex, Z is in the complex numbers, it's of the form A plus IB. A is called the real part, B is called the imaginary part, I is the square root of -1. It's over A and up B. This is basically rectangular coordinates. Now, this is a number system. You can add, subtract, multiply, and divide in it. And a lot of math and a lot of physics is done with it. Tesla did alternating currents, unlike his mentor and cheater, Thomas Edison. Thomas Edison made all his motors and this and that with direct current. Tesla had the brilliant idea of using of alternating current, and it turns out the math for alternating current is complex numbers. All right, so to add in complex numbers, you combine like terms. A plus IB plus C plus ID is A plus C plus I times B plus D. You have the real parts and the imaginary parts separately. Subtraction is much the same. A minus C plus I times B minus D. Complex multiplication is a little more complicated. I use the first outer inner last rule, and I squared equals -1. So A plus IB times C plus ID. First is A times C. Outer is A times ID like this. Inner is I times B times C like this. Last is IB times ID, but I squared equals -1, so you get minus BD. And you shuffle it around a bit to get AC minus BD plus I times AD plus BC. Okay. And by the way, this minus here is sort of related to that awkward minus sign when we're doing the sums to product rule and the product to sums rule. It's off. This is one of the awkward eccentric ones. 1 out of 3 has a negative sign for this reason. It ties into complex numbers. Now, okay, since we have talking about rectangular and polar forms, it applies to complex numbers as well. If you have a complex number A plus IB over A and up B, it's also r to distance r and an angle theta from the positive real axis. So, okay, we'll say that A is r cos theta, B is r sine theta. So you put it together, r equals z cos theta plus I times r sine theta. Remove a common factor of r and get r times cos theta plus I sine theta. This writes the complex number with the radius part and the theta part separated, so you can think of them separately. R is the radius, root of a squared plus b squared, how far the point is from the origin. Theta is the angle from the positive real axis. These are polar coordinates for z. Now we'll give a special name for this thing. Cos theta plus I sine theta is called cis theta, C-I-S. It's also related, the same word cis is used in chemistry and in other areas as well. Cis theta is a point in the unit circle in the complex plane. It's out at distance 1 and it is angle theta. As theta increases, it spins around the circle. So, rectangular form for z is A plus IB. Polar form is r cis theta. Now, rectangular form is very good for adding and subtracting complex numbers. You just do the real and imaginary parts separately. But multiplication in rectangular coordinates is a little more complicated. Well, it works the other way around for multiplication. Turns out that r cis theta is really very efficient for multiplying complex numbers. Here's how it goes. We'll start by multiplying cis alpha with cis beta. What is it? Well, cis alpha is cos alpha plus I sine alpha, times cis beta is cos beta plus I sine beta. And then you multiply them out and do churn through the arithmetic, and you'll get cos alpha cos beta minus sine alpha sine beta. That's the real part, plus I times sine alpha cos beta plus sine beta cos alpha. That's the imaginary part. Now this, if you look back a couple chapters, is the formula for adding angles with cosines. Cos alpha cos beta minus sine alpha sine beta is cosine of alpha plus beta. And this, sine alpha cos beta plus cos alpha sine beta, is the angle addition formula for sine. It's sine of alpha plus beta. So you get cosine of alpha plus beta is plus I times sine of alpha plus beta. So this is cis of alpha plus beta. So cis alpha times cis beta equals cis of alpha plus beta. Cis turns multiplication into addition. Now, if multiplication of cis's add the angles, then dividing cis's is subtract the angles. Cis alpha divided by cis beta is cis of alpha minus beta. And since powers are repeated multiplications, then cis alpha to the nth power is a multiplication of the angle, cis at n times alpha. Now, if we go back to the polar coordinate for complex numbers, it makes it very easy. We have r cis alpha times s cis beta. You multiply the radii, rs, times cis of alpha plus beta. So you multiply the angles, so you multiply the lengths and add the angles. R cis beta divided by s cis beta, well, we divide the lengths, r over s. Cis of alpha minus beta, you subtract the angles. If you take an nth power of r cis alpha, then you take a power of the radius, r to the n, and you multiply the angle, cis n alpha. So here's how it will work. If this point is at r cis alpha, and this point is at s cis beta, here's an angle, radius r, radius s, angle alpha, angle beta, then their product, ZW, is rs cis of alpha plus beta. You multiply the lengths, and you add the angles. This, incidentally, was why Tesla found it useful to do the arithmetic, the mathematics of alternating currents with complex numbers. All right. Now, we've added, subtracted, and multiplied and taken powers of complex numbers. Now about complex roots, a little more complicated, mostly because there's generally going to be more than one solution. So let's say we want to solve w to the n equals r cis alpha. We're given r, we're given alpha. What w has nth power equal to r cis alpha? Well, we'll call it s cis beta and see what happens. So s cis beta to the nth power equals r cis alpha. So s to the n cis n beta equals r cis alpha. Okay, these have the same length. S to the n equals r. So s is nth root of r. Now, n beta and alpha point to the same direction. So they're equal plus an integer multiple of rotations. If you spin around more than once, you wind up pointing in the same direction. So n beta equals alpha plus an integer multiple of rotations. N beta equals alpha plus 2 pi k, k being a whole number. You divide by n. Beta is alpha plus 2 pi k over n. So there's your nth roots of n r cis alpha. Nth root of r cis of alpha plus 2 pi k over n, where k is a whole number, 0, 1, 2, 3, up to n minus 1. N possible solutions, in other words. So here are some examples. 4 minus 4i, what's its polar form? Well, let's graph it. It's over 4 and down 4. Here's the radius r, root 4 squared plus negative 4 squared. That's 4 root 2. This is isosceles, so this is a 45-degree angle. Negative 45 degrees because it spins clockwise. So it's 4 root 2, cis of negative 45 degrees. That's the polar form of this 4 minus 4i. Let's go the other way. 2 cis 120. What's its rectangular form? Well, you turn it 120 degrees from the positive x-axis. That's 60 degrees here. Go out a distance 2. So this side will be 1. Well, sorry, this side will be 1. Really minus 1. And this side will be root 3. So minus I plus I root 3. Here we have Z is 2 cis 40 degrees. W is 4 cis 20 degrees. What's their product? What's their quotient? Leave it in polar form. Their product, well, you multiply the lengths, 2 times 4. Cis of, add the angles, 40 plus 20. So you get 8 cis 60 degrees. Their ratio, well, you divide the lengths, 2 divided by 4. And you subtract the angles, 40 minus 20. So you get 1/2 cis 20 degrees. Here we have, here we're given the Z and W in terms of rectangular coordinates. Find the polar form of their product and their quotient. Okay, Z is 2 plus 2I, W is root 3 minus I. 2 plus 2I over 2 up to diagonal is 2 root 2, angles 45 degrees. So Z is 2 root 2 cis 45 degrees. W is over root 3 down 1. Its radius, the diagonal is 2. This is a 30, 60, 90 triangle. This will be a negative 30 degrees. They're negative because it's clockwise. And so W is 2 cis of negative 30 degrees. Okay, their product. Well, 2 root 2 times 2 is 4 root 2. 45 degrees plus negative 30 degrees is 15 degrees. So their product is 4 root 2 cis 15 degrees. Their ratio, 2 root 2 divided by 2 is root 2. 45 degrees minus negative 30 degrees is 75 degrees. So Z over W is root 2 cis of 75 degrees. Now, we have the third power of 4 cis 40 degrees. That's for rectangular form. Okay, first we take the third power of 4 and take the 40 degrees times 3. 4 to the third is 64. 3 times 40 is 120 degrees. And cosine of 120 degrees is minus 1/2. Sine is root 3 over 2. So it's 64 times minus 1/2 plus I root 3 over 2. Multiplying through by 64, you get negative 32 plus I 32 root 3. Here we have a fourth power of root 5 cis 3 pi over 16, again, in rectangular form. Okay, first we take a fourth power of the square root of 5. We take cis of 4 times 3 pi over 16. Now, fourth power of root 5 is 5 to the 4 halves, which is 5 to the second, which is 25. 4 times 3 pi over 16 is 3 pi over 4. Cosine of 3 pi over 4 is minus root 2 over 2. Sine of 3 pi over 4 is root 2 over 2. Then multiply by 25, you get negative 25 root 2 over 2 plus I times 25 root 2 over 2. Here they ask for the fifth power of 1 minus I. Okay. 1 minus I is over 1 down 1, so the diagonal is root 2 and the angle is minus 45 degrees. So this is the fifth power of root 2 cis negative 45 degrees. So it'll be root 2 to a fifth power, cis of 5 times negative 45 degrees. So that's 2 to the 5 halves, or 2 squared, 2 to the half, or 4 root 2. 2 minus 225 degrees, we add 360 degrees is 135 degrees. And that lands you in the, let's see, is that the second quadrant? Yes. So, and cosine of 135 is degrees is minus root 2 over 2. Sine of 135 degrees is root 2 over 2. Multiplying throughout by 4 root 2. The root 2 and the 2's cancel, and you get minus 4 plus I times 4. Now here they ask for a square root, a fourth root of a complex number. Find the fourth root, or fourth root's plural, of 4 minus I 4 root 3. Okay. 4 minus I 4 root 3. It's over 4 and down 4 root 3. That's a 30, 60, 90 triangle. The diagonal is 8. You can work out the angles, negative 60 degrees. So W to the fourth is 8 cis of negative 60 degrees. So to solve this, we take a fourth power of the length and 1/4 of negative 60 plus 360k over 4. So, all right, so 8 to the 1/4, 8 is 2 to the 3rd, so this is 2 to the 3/4. And then dividing through by 4, get negative, consists of negative 15 degrees plus 90k degrees. So, for example, this is out a distance 2 to the 3/4. Here's at an angle negative 15 degrees. At another 90 degrees, this is at 75 degrees. At another 90 degrees, this is at 165 degrees. Another 90 degrees is at 255 degrees. So you get these four fourth roots. Here they ask for find the complex fifth roots of I. So w to the fifth equals I. Well, I is 1 cis 90 degrees. So w, to find w, take the fifth root of 1, cis of this plus rotations over 5. Cis of 90 degrees plus 360k degrees over 5. And fifth root of 1 is 1, and dividing through by 5, you get 18 degrees plus 72k degrees. Getting out of my way. So this will be cis 18 degrees, or adding 72, you get cis 90 degrees, or cis 162 degrees, or, excuse me, cat, cis 234 degrees, or cis 306 degrees. 18 degree, cis 18, cis 90, or in other words, I, because I to the fifth equals I. Cis 162 degrees, cis 234 degrees, cis 306 degrees. These are located in a regular pentagon. So there you have it. Okay.